The universe we know is a triumph of deduction. We know how the first galaxies ignited. We know how atoms formed. We can rewind time to a fraction of a second after the beginning of everything. And yet, when we ask the simplest, most fundamental questions, we still have no answer. Here are 8 mysteries that science, for all its genius, still cannot solve. For nearly a century, cosmology has rested on one premise: the universe is expanding. Edwin Hubble saw it first: galaxies fleeing from us. Calculating the exact speed of this escape became the holy grail. We call it the Hubble constant, and that's where everything goes wrong. We have 2 methods to measure it. The first looks at the early universe, the cosmic microwave background, the echo of the Big Bang. The Planck satellite gives us one number: 67 kilometers per second per megaparsec. The second method looks at the nearby universe, pulsating stars, distant supernovae. The Hubble telescope gives us another number: 6 kilometers per second. It sounds trivial. For years we told ourselves someone made a measurement error, but the error bars shrank. The divergence crossed the 5 sigma threshold, the gold standard in particle physics for declaring a discovery. The problem isn't in the instruments, it's in our equations. Our standard model of cosmology, the framework that explains the evolution of everything from atoms to galaxy clusters, might be broken. If you add up every star, every planet, every nebula, and every black hole in the observable universe, you've accounted for only 5% of reality. 27% of the cosmos's energy budget is made of a substance that refuses to interact with light. We can't see it. We can't touch it. It emits nothing, absorbs nothing. We only know it exists because of its gravitational footprint, overwhelming, undeniable. Stars at the edges of spiral galaxies spin far too fast. Without an invisible mass holding them back, they should be flung into the void. Galaxy clusters bend light from distant objects through gravitational lensing, far more than visible mass allows. We've built detectors buried under kilometers of rock, shielded from cosmic rays. Vats of ultra-pure xenon, waiting for a dark matter particle to strike a nucleus and produce a microscopic flash. We've smashed protons together at the Large Hadron Collider, hoping to create a dark matter particle in the chaos of the collision. Silence. Every detector has stayed mute. We can map the invisible web of dark matter across billions of light years, dictating galaxy formation, structuring the entire cosmos. But we cannot hold a single fragment of it in a laboratory. The ghost remains purely gravitational. In 1998, 2 teams of astronomers set out to measure the deceleration of the universe. The logic was simple. Since the Big Bang, the gravity of all matter should be slowing the expansion, like a cosmic brake. They observed distant supernovae to calculate this deceleration. The data said the opposite. The expansion wasn't slowing down. It was accelerating. This discovery, which won the Nobel Prize in 2011, introduced an entity no one had predicted. A repulsive force permeating all of space, countering gravity at the cosmic scale. We called it dark energy. It makes up 68% of the universe. And here's the most unsettling part. Dark energy doesn't dilute as space expands. The more the universe grows, the more dark energy there is. It's a runaway train. If this acceleration continues, in billions of years, every galaxy beyond our local group will have vanished behind a cosmological horizon. Their light will never again reach us. A future civilization will look at the sky and see only absolute void, with no evidence that other galaxies ever existed. The math insists we should not be alone. The Milky Way contains between 100 and 400 billion stars. The Kepler telescope proved that planets are the norm, not the exception. Tens of billions of rocky worlds orbit in their star's habitable zone, where liquid water can exist. Our solar system is young compared to the galaxy. Countless potential civilizations had billions of years of head start on us. A single one of them, traveling at a fraction of light speed, could have colonized the galaxy in a few million years. And yet, our radio telescopes listen, and the cosmos remains absolutely silent. No Dyson spheres capturing the energy of entire stars, no radio beacons crossing the interstellar void. Nothing. This contradiction between the overwhelming probability of extraterrestrial life and the total silence is the Fermi Paradox. The explanations are as varied as they are uncomfortable. The Great Filter, somewhere between the first cell and interstellar colonization, there exists an obstacle almost no one clears. The chilling question, is this filter behind us or ahead of us? The zoo hypothesis. Advanced civilizations observe us but enforce a non-interference policy. Earth as a nature reserve. Or the loneliest possibility, we are simply the first. The universe spent its first several billion years manufacturing the heavy elements necessary for life. Perhaps Earth is one of the very first cradles of consciousness in the cosmos. The galaxy is not empty. It is waiting. There exists a boundary in space where the laws of physics collapse. When a massive star implodes, its gravity becomes so intense that nothing, not even light bursts, can escape. This is the event horizon. But the real mystery isn't at the boundary, it's at the center. Einstein's general relativity says that all the star's mass crushes into an infinitely small point, a singularity, zero volume, infinite density. The equations produce mathematical nonsense. The problem is that relativity is only half the physics textbook. The other half, quantum mechanics, explicitly forbids a singularity. Heisenberg's uncertainty principle says you cannot simultaneously know a particle's exact position and velocity. Crushing matter into a mathematical point of zero dimension violates the foundations of quantum reality. We have two theories of reality, both extraordinarily verified, that contradict each other at the heart of a black hole. To resolve this requires a theory of quantum gravity, a mathematical bridge explaining how gravity works at the microscopic level. Decades of work on string theory, loop quantum gravity, and still no answer. The interior of a black hole remains the ultimate locked room. In 2007, an astronomer sifting through archival data noticed an anomaly, a spike of radio energy lasting only a few milliseconds, but containing as much energy as our sun emits in a month. By measuring the dispersion of frequencies, she calculated its origin. This signal had traveled billions of light years. It was the first fast radio burst. For years, no one could explain what was generating these flashes of unimaginable intensity. The mystery deepened when we discovered that some bursts repeat, ruling out one-off events like supernovae. Then in 2020, the breakthrough. A burst came from our own Milky Way. We traced it to a magnetar, a neutron star with a magnetic field trillions of times stronger than Earth's. But the case isn't closed. The local burst was far weaker than the ones we detect from the distant universe, and some repeating bursts show complex cycles, days of frantic activity followed by weeks of dormancy. A simple stellar quake doesn't explain this precise choreography. Is it a single phenomenon with variable intensity? Or does the term fast radio burst cover several completely different mechanisms? The cosmos flickers with extreme energy every few seconds, and we're only beginning to map the celestial engines producing them. Our galaxy is not stationary. It's hurtling at 600 kilometers per second through space. And it's not alone. Hundreds of thousands of galaxies, our entire supercluster, Laniakea, are being pulled in the same direction, toward a point we cannot see. Astronomers call this point the Great Attractor. It lies somewhere behind the zone of avoidance, a region of sky obscured by the disk of our own Milky Way, where dust and stars block our view. It's like trying to see through a wall of cosmic fog. Thanks to radio telescopes which pierce the dust, we've begun to glimpse what's hiding there. The Norma Cluster, a massive group of galaxies, but calculations suggest it's not enough. Even this cluster cannot explain the full pull we're experiencing. Behind the Great Attractor, there may be something even more massive. A structure we haven't yet mapped. Our galaxy, our supercluster, everything we know, in freefall toward the invisible. And so we arrive at the ultimate question. The standard cosmological model is a triumph. We can describe the evolution of the universe with stunning precision. We know how the first atoms formed, 380,000 years after the beginning. We can model the nuclear fusion that occurred 3 minutes after. We can push our mathematics to 10 to the power of negative 43 seconds, the Planck time. And there, everything stops. The laws of physics collapse. Temperature and density become so extreme that relativity and quantum mechanics tangle in incomprehensible ways. We cannot mathematically define what the universe looked like at time zero. So attempting to answer what happened before time zero, that is the deepest, most impenetrable question in all of human inquiry. Physicists propose hypotheses. Eternal inflation, our Big Bang was not the absolute beginning, just the local birth of our cosmic bubble in a vastly larger multiverse, perpetually inflating. Cyclic models, the universe is born, expands, contracts into a big crunch, then rebounds into a new Big Bang, an endless sequence. But Stephen Hawking offered the most unsettling answer. Asking what happened before the Big Bang, he said, is like asking what lies north of the North Pole. Time itself did not exist before the universe. There is no before because the very concept of before is a property of the universe, not a container the universe appeared in. It's mathematically elegant and deeply unsatisfying to human intuition. Our brains evolved to understand causality. Every effect must have a cause. Confronting the absolute boundary of time forces us to accept that causality itself may only be a local phenomenon, an emergent property of the specific universe we inhabit. We stand at the edge of Planck time, facing the mathematical void, searching for words to describe the ultimate origin of existence. 8 questions, 8 locked doors. And the most remarkable thing, it's not that we have no answers. It's that we know precisely where our knowledge stops. Each mystery is an invitation. Each unknown is a beacon guiding the next generation of telescopes, of detectors, of minds. The universe isn't strange because it hides monsters. It's strange because it's vast and ancient and indifferent. And every so often, it shows us something we cannot yet explain.